In the chat, please.
Okay, I am going. I think now you should be able to see my presentation. Is loading. I hope so. Yeah, now it should be working. Okay, so um, we decided to present this study because a study with a very sound database and with a lot of data, and actually something that we usually see in the industry so much, and it was very special. But actually, some of this data turned out to be kind of problematic and leading to more problems than solutions, and those is the point where we have been asked to do this study. So I'm presenting this is a study that we did a couple of years ago together with Mario Habermüller, and basically the 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 study we're going to discuss basically an introduction on what were the objectives, why we were involved in this study, and then the methodology and data availability, why we decided to do that, and why it stops. Okay, did it stop my presentation? Because suddenly I don't
Yes.
see it anymore.
Yeah,
Sorry.
please restart it, Nicola.
Okay, I started again. Sorry.
There it is. Thank you.
Okay. Okay, now it should be working. Okay, so methodology and data available for this study. It was really hell a lot of data, and something that is the reason why we decided to do it. Then something on the MHF test that they acquired, which also is interesting because they were kind of providing some debatable results. And then we will see the drilling experience and integration with the image logs to see how to use this and to get the best results. And then finally an integration of all the data available and the conclusion. So let's start with the introduction. This study was performed within a large campaign to characterize the subsurface geology of a waste storage in an underground waste storage site in Europe. And the client was acquiring an enormous amount of data to characterize this, and we were invited in various parts of this project. But one of the main targets of this campaign was to have good boreals in order to run as many different kind of tests to acquire a sound database. And thus they started drilling with a slightly overbalanced mud weight in order to minimize the risk of boreal breakout. Okay, and we were not involved in this stage yet when they started this campaign. So they were drilling basically 9 deep boreals, more than 1,000 meters deep, drilling from the surface to somewhere to the basement at depth. And they will do 8 vertical wells, 1 deviated. And basically they acquired an extensive amount of data. In particular, they were coring nearly entirely from the surface to the boreal bottom in almost in every boreal. They were acquiring different image logs with acoustic and resistivity images in different runs, even after performing the micro fracking. And we were invited also doing the rush job analysis of this and also the post MHF analysis. And basically they were acquiring an enormous amount of data, really, really sound. We have never seen such a sound database in an oil project. They acquired also image logs and MHF tests, so microfracking tests nearly in all the wells. We were not doing the interpretation of the MHF, but we received already interpreted MHF. We're actually just doing the review of the after fracking test in the initial part of this test. So, and then as soon as they started drilling, they experienced several mud losses, sometimes even massive, and including one in the formation where the storage was planned. So that led to some panic because, of course, you don't want to have losses, potential permeability in the site that should be tight. So, of course, mud loss can occur due to very different reasons. One, very simple, if the mud pressure in the borehole is higher than the formation pressure. And in that case, if you have also porosity and permeability in the host rock, then some of the fluids might migrate into the rock. And then that would be an indication for primary porosity and permeability. Or if the mud gradient, basically the pressure, the static pressure in the borehole is larger than the fracture gradient, and then you would generate an artificial fracture, a hydraulic fracture in the rock, and the fluids would migrate into the rock. So both these two processes result into mud losses, but the process is very different. Okay. So some of the mud losses occurred, of course, during coring, including one very disappointing because they saw that one fracture was in the core and it was also in the images. And one of the first things that you learn when you do the course of structural geology is that if you see a fracture in the core and also in the images must be natural. And this led to several issues because, of course, this has been interpreted as natural by the core loggers. And of course, that resulted into several investigations. They involved multiple people to try to understand what was really going on in this formation, if the fracture was actually natural or not. And if the site was suitable for the nuclear waste storage. Because, of course, if you have natural fractures, open natural fractures at depth, in the site where you want to store the nuclear waste for thousands of years is something that is, of course, not feasible. For this reason, the project was slow it down, and they invested some time and invested some resources to try to understand what happened here. And we were asked also to take a look at the data to try to see if we could find discover exactly what happened in this specific interval. But we analyzed also all the other wells because they experienced losses more or less in 2 or 3 thirds of the wells, so that we were also trying to understand why that happened and if that was potentially a problem for them. Okay, so the methodology, we started basically with the log interpretation, image log interpretation. We say micro-resistivity and acoustic logs, of course, to identify induced fissures so that you should see, and also to detect the natural fractures, because the natural fractures, as we have seen before, if you have natural fractures, the loss might go into the natural fractures. Otherwise, you look for hydraulic fracturing. So we started with the image logs. The second information that we had were the cores. So as they were basically coding from top to bottom, we had thousands of meters of cores, and luckily they have been already interpreted and analyzed by the structural geology, and we received just the data already depth shifted and restored for the original orientation of the core by the company, the client, and we loaded the three-dimensional 3D core scans next to the image logs so that we could correlate one-to-one what was seen in the images, what was seen in the core, and also comparing the interpretation from the core and interpretation from the images, so that we could kind of try to figure out what we were seeing, basically. And then we received the interpretation, of the AMHF So not the raw data, the data have been interpreted by another party, and to further characterize the geological model. And turned out that these MHF were not 100% convincing due to several reasons that maybe we will see later on. So, and then the methodology was basically based on the analysis of the drilling history, that when under which circumstances happened the losses, and then we were going along these images to try to figure out in the open hole log section what happened and which features could have led to these losses. And I mentioned it before, as these were all open hole, they had a quite long open hole section. Losses were reported, of course, at the depth of the drill bit, but they could have happened anywhere between the drill bit and the bottom of casing, so that because in particular, if you are changing the pressure in the borehole, you can start losing fluids in an interval where previously was not happening. So this, luckily, we had all these image logs and cores, so that we could go back to our interpretations and try to link the losses to the actual features and try to understand if they were natural or not. Okay. And then for some of the wells, and in particular for the interval where we had this specific fracture in the well that was seen in the core and in the images, and so that led them to several to panic basically. We're doing also detailed analysis of the drilling reports and also the high resolution standpipe pressure data and drilling parameters and whatever we had to try to really nail down what happened in that well. Okay. So as I say, the MHF were given to us already interpreted, and we immediately see that these are different wells in different depth ranges, and also the geology is similar, but it's not the same. So, for example, the thickness of this interval is not the same in all the wells, and some are deeper, are located in different parts. But immediately you see that there is a dramatic change in all these wells. Some are more or less, they show kind of a constant gradient, others are more scattered, and also some have some values which are very high compared to the rest. And this we realize immediately that these data were problematic because they were higher than the vertical stress at that depth. So that means that is something that this cannot be. So there were some issues in this MHF, and later on we discovered that probably the issue is that due to the depth that is not very high, the technique we use it for the MHF interpretation is should be adjusted, and because of there was some research in this direction due to other similar projects in France. Now they refined this method, and now this is a bit different, maybe will be a little bit different, but you can see that these data are also scattered within the wells or within the same formation with some very scattered data, which maybe to some extent reflect the actual geology, the actual information, and maybe to some extent are due to some potential overestimating. So if you look in the map view, we have basically about this 35 kilometers long study area. We have two wells here where you have the highest, these are average fracture gradient, which is something that you should not do, but just to give you a quick and dirty analysis of what we are dealing with. So you see here that here we are about 24 megapascal per kilometer. In the central area, we have completely different values. In particular, back one is the well with the smallest average fracture gradient. And this is actually the well where they had this unintentional potential hydraulic fracture. And this is not surprising due to this value. And then here we have another cluster where we have some kind of similar to the other thing. So we see that already the stress is changing from place to place. Okay, even though we were not asked to do a full geomechanical modeling that was done by another company and was not available at this time, we use this information to try to understand what happened in the boreal. Just not to do the full geomechanical model, but just to use this information for the latest study. Okay, so this is what this is exactly what what I learned from David Martinez, who is also going to present something here. And thank you, David, for teaching me how to use this stuff. So this is basically we did this for all the wells. I'm going to show you just a couple of them where we have something. Is the depth? That is the depth, and these are all the accidents or the events, coring, losses, formation integrity tests, AMHF, whatever they were doing in the boreal. And then we have the red line is the mud weight that they were using, mud weight and mud type that they were using during the. Oh no, it happened again. Oh, why? Sorry. I don't know why it's once in a while it gets out automatically. Okay, no, sorry, I restart again. Okay, okay, I go to this slide. Now you should see it again, right? No?
Yes. Yes.
Oh, sorry.
Yep, you're good.
Yeah, you're all good. Thank you.
Sorry. So basically, that is in this well, for example, we didn't have any losses, and so there is nothing to be seen. Here we put the stratigraphy. We see what we see in the boreal, and this is basically the what we do as a drilling experience plot for all the wells. Okay, we pass to the next well. This is actually already a well where we have some losses, and it's nearby to the other well. And we see that, for example, we have losses in this interval and losses in the lower part. And this is we can see here the mud weight that they were using and the different conditions. And we are going to look at the corresponding interpretation. Here I summarize the conditions. This is the standpipe pressure. So in this interval, for example, here we are in the carbonates. In the Malm, it's a very fractured reservoir. It's actually used for geothermal activities in this part of Europe, and is a well-known fractured reservoir. So we immediately identified that this open fracture, which is also on the core. This is always the acoustic, the static images, and this is the core. In that case, we could nail the losses to this specific fracture. We could say there is no hydraulic fracturing in this well. So in the next one, this is also another seal in the lower part of the same well is another fractured carbonate in the same actually much deeper. In this interval also they didn't have so many losses, 12 cubic meters, and here the losses started when the drill bit was at 1,121, but actually they started a bit higher, where we could see these open fractures that are also detected in the cores. So in this case, it's one of these examples where they were drilling with a regular mud weight and nothing happened, and then as soon as they started, they raised the mud weight to 121, which they had to do before drilling the section below where they have also some salt. Then they had to use a salt mud, much higher mud weight, and the losses started because at this point the pressure in the boreal was larger than the formation pressure at this interval was large enough to start migrating in the formation. Also in this case, those we don't have any hydraulic fracturing in this well. So now we go to the most problematic well. they still have nightmares when they hear this name because they struggled so much. So losses, they had losses in the upper part, in this formation, which is actually the interval where they want to store the nuclear waste, and the losses in the lower part. So we start with the losses in the lower part because that is easier. It's the same interval that we have seen before. So the same fractured carbonates. This is naturally fractured. We see the fractures in the images, in the acoustic images, and also in the cores. They are, again, as soon as they rise at the mud weight to drill the lower section, the losses started. Losses were quite massive in this interval, 675 cubic meters, because they couldn't stop them, basically, because they had to keep this mudway high to drill the lower part. And so for a few days or maybe a week, they kept losing fluids in this formation. But the real nightmare was this part over here, okay? And now we see it. So that is basically in this interval, basically we have this is the image logs in the interval where they had losses. So if I had only the image logs, I would not have any problem saying this is an hydraulic fracture. So it's very long, about 50 meters long. In this part is perfectly vertical, parallel to the border wall. It looks like a centerline fracture, and then extends into this part with the sinusoid and the upper part with sinusoid. However, unfortunately, the fracture was seen also in the core, or better, in part of the core, because the fracture is seen only in this lower part. These are the core segments, and actually, if you look, this is the fracture is seen only in this core segment. And because the fracture was seen in the core, it was considered by various people, actually, and some people, they still believe it, that this was a natural fracture. And so just to explain what they were really doing in this interval, here you have the core segments. These cores are very short, a few meters. In order to preserve the core, they were cutting one core, bringing it to the surface, lowering the corer, cutting one core, bringing it to the surface, and so on. So they were drilling quite slowly and going down, acquiring 1, 2, 3, 4, 5 cores. And at this point, when they were here, they started having losses. And clearly, the fracture propagated down at the border wall. So the fracture propagated in the border wall, and then when reached the bottom of the wall, well, at that time propagated down in the formation below, and then at one point it deviated. So when they cut the next core, they recovered this induced fracture that actually shouldn't be in the core, according to the manual. So then we are looking in detail at this interval, so we could really see exactly when the fracture was formed, because it was formed between cutting the time when they were cutting this and the time when they were cutting this. That is about a couple of hours. So we went through the reports, and we were looking at each in activity they were doing. This is time. So here they were cutting this core, bringing it to the surface, lowering the pipe, cutting one core, bringing it to the surface. And this is the interval where losses started. No? So we're looking at this part of the data and try to figure out what might have happened. And this is the core where the fracture was seen. So the first thing, here I put the mud density, and here I computed just the mud density basically was the same. And the static mud density, that is not so, that is not so, not changing so much. It's just changing for these few meters that we are going down when we are going down. This is the standpipe pressure, and you see that you can, so the standpipe pressure, I don't know why, they don't know themselves, but at one point here is very low, the value, and 1 point here they were for a couple of hours it was higher, and this is exactly when the fracture occurred. And this is then it was going down again. And this is the let's say the fracture gradient computed from the MHF in that area. These are the two MHF that we have, are a bit higher and one is below. We don't have data exactly in this part, but I interpolated between these two values, and I estimated this value, just not to say that this is the actual fracture gradient, but this is to say if that is a reasonable range for the actual gradient. So if I estimate, if I take the standpipe pressure and the mat pressure, and I put them together, even without considering the drop of pressure due to the movement of the mat down to the border, so it means that the actual pressure is not the standpipe pressure, but less. So with these two, we will reach 126 bar at this depth, and which is smaller than the fracture gradient estimated from the MHF. But as I mentioned it before, so it's not that far away, but it's maybe 20 bars below, and considering that this is actually overestimated, probably the fracture gradient is smaller than this, and that is exactly what I was showing you, what I was telling you before, that in this shallow depth, the MHF tend to be a little bit overestimated due to the way we compute this. Because of course this fracture is an hydraulic fracture, and the static, let's say the static mat pressure is rather well constrained, and so the issue is probably in this estimation. So, but sorry, again, luckily we managed to convince them that this was not a natural fracture, but actually an hydraulic fracture, even though it was a really nightmare for them, as they had to drill a site. They lost a tool in this interval, and they had to drill a side track, so it was really becoming kind of a nightmare. Okay, so that is another example. This is another well where we have 3 intervals with losses. We start with this at 240. This is in the upper part, in this fracture carbonates. In this specific case, even though they were drilling with a kind of very light mat, they had hydraulic fracturing, and we have this long fracture that is not visible here in the course. The losses were not very high, but still significant. And then we have another interval here where they had also not significant losses. Here still due clearly to hydraulic fracturing. Here we don't have any evidences for natural fractures in the core. And so in this well, again, here actually they started with a quite high pressure, mud density, and then as soon as they, in the report, they clearly see that they write at one point they rise the standpipe pressure for some reason, and 2 seconds later, this losses started. So interesting. So conclusions for this study. Okay, first of all, we have seen that losses occur through natural fractures in some of the wells. I'm not going to present. This is some summary for all the wells, even those which I didn't present you, because after a while it's a little bit boring. You see always the same things. So basically, we have losses in the natural fractures, only in the fractured limestones, or sometimes also in hydraulic fractures, and sometimes we have a combination of two, because sometimes we have hydraulic fracturing and leading to that probably connecting to natural fractures where actually significant losses occurred. And then we have hydraulic fracturing in these two wells, and then actually we have in one or two other wells which are not in part of this study because of time constraint. So basically, what we have seen is that also the MHF gradients at this shallow depths are very variable in the area, suggesting that maybe we have heterogeneous stress field, also very variable in the individual wells and even in the stratigraphic intervals. And also we have seen that some of the MHF tests might be overestimated. I introduced this conclusion because recently we have done another study for similar project where they have very shallow MHF tests and they are systematically overestimated according to their engineer. And then in many cases, hydraulic fracturing occurred with a combination of subcritical but close to fracture gradient static mud pressure and plus excessive standby pressure that leads basically to the onset of hydraulic fracturing. Probably if they were controlling the standby pressure more, they would have avoided that, even though they were very close to hydraulic fracturing. So in BAC1, which is the well where we have seen this interesting natural, non-natural fracture, the static mud pressure and SVP are very close to the magnitude of the MHF. However, is actually smaller. That suggests what you have seen before, that probably the MHF are overestimated. And clearly, we can nail the onset of this fracturing to a very accurate time frame, a couple of hours between the end of cutting core 98 and the cutting of core 99, where the fracture was seen. And I will add another conclusion here, is that don't trust too much the fractures that you see in the course, because sometimes might be also induced, even though they look not like natural. And so that proves that the interval is actually suitable for the nuclear waste storage, and they were very happy to know that they can go can then proceed with this project also in the future steps. So, and the losses occurred in lateral fractures in many intervals, in intervals much higher than the drill bit at that time, when the mud weight was raised. And that means that the integration of the image logs and of the core data with the drilling data provided a very important tool to fully constrain in which intervals the losses occur, and also to try to figure out if these losses were hydraulic fracturing or not. So basically, we should thank you, Nagra. Nagra is the company that is responsible for the development of this radioactive waste disposal in Switzerland, for allowing us to do this interesting study and to share this data with you. Thank you.
Thanks, Nicola. Let's have maximum 3 questions. Al, I see you first with your hand up. What's your question, please? Al, can you unmute yourself?
Sorry. you were showing great examples of pedal centerline fractures, which are a well-known phenomena, and it's very easy to distinguish them from natural fractures by looking at the fracture surface morphology. And I mean, this has been known since the 1970s. I'm amazed that that people aren't more familiar with these with basic fractography and core and what these things look like in image logs. I mean, these were just textbook examples.
Correct. But the approach was okay. That was also the opinion of another consultant that was a structural geology, went there and looked at the fracture and was classify this as induced fracture. However, the thing that the fracture was not visible in the rest of the core, because usually when you look at the core, you see that the fractures form from the center and then they deviate. This in that interval was not so obvious because there was very little part that was like parallel to the core axe. It was more inclined. That I think that was the reason why. But I was not involved in that part, so I really don't know why they did it. Yeah.
Right. Well, I mean, centerline fractures form ahead of the bits, so they wander around. Right. They form in front of the bits. That's why you see them in the core and the image. Yeah, but it's also why their orientation is they don't track the borehole always perfectly because they're propagating ahead of the bit. Okay, that's all for me.
Okay.
Thank you. Any